Now let's see few examples. Here I have the first question. See the question. Given A is equal to set 1, 2, 3, 4, 5 and 6 and R is a relation from A to A, where R is defined as set of ordered pair xy such that y is divisible by x. Y is divisible by x. And for all x comma y belongs to where? Definitely it belongs to the set A. Okay. So now I am going to check whether the given relation is a equivalence relation or not. Okay. So what all I need to think about? I need to think whether it is reflexive. I need to find whether it is symmetric as well as whether it is transitive also. So let me check for whether the relation is reflexive. Now, before I move on to this relation, let me write what are the ordered pairs that falls under this relation in its roster form. So that is very clear for me to understand whether it is reflexive, symmetric and transitive. Okay, take the ordered pair 1, 1. Is 1 divisible by 1? Yes or no? Yes. So definitely the ordered pair 1, 1 comes under the or satisfies the given relation. What about 2, 2? That also. Likewise I can say 3, 3, 4, 4, 5, 5 and what about 6, 6? Definitely 6 is divisible by 6. Now, next one what I am going to consider is 1, 2. 2 divided by 1. Is it possible? Can this 2 be divisible by 1? Yes or no? Yes. That means 1, 2 is satisfied by the relation. What about 1, 3, 1, 4, 1, 5, 1, 6? Definitely. All these satisfies the given relation. Then what? Then you have 2, 4. Isn't it? Then you have what? 2, 6. Right? Then you have 3, 6. Anything more? Is there anything more? By taking two elements from this set and the divisibility, checking the divisibility, can you find anything else? No. So these are the possible ordered pairs that can fall under this relation. So now all the elements in the relations are now for us, it is easily visible. Now I can just check for reflexive. So to check for reflexive, to check whether the function is reflexive. See, in order to make the function reflexive, for all A belongs to capital A, for all elements that belongs to the set A must belong to the relation. So here all the elements are what? 1 to 6, 1, 2, 3, 4, 5 and 6. Do you have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6? Yes. That means this relation is reflexive. Reflexive. So this is reflexive, definitely. Now let us check for symmetry. Symmetry means what? You have 1, 2. Do you have 2, 1 here? Check out. Do you have 2, 1 here? No. You have 1, 3. Do you have 3, 1? No. 1, 4. Do you have 4, 1? No. So if any one of the elements, if 1, 2 has 2, 1. Then also 1, 3 doesn't have a 3, 1 here. So for every element, for all AB that you take in the relation, you must find BA. But here that is not there. So R is not symmetric. R is not symmetric. Okay? R is not symmetric. Now coming to transitivity. Checking for transitivity. 1, 2. Do you have 2, 6? Yes, I have 2, 6. Then do I have 1, 6? Check for that. 1, 6. Yes, I have a 1, 6. Right? Then 1, 2, 2, 6, 1, 6. 1, 3, 3, 6. Do I have a 1, 6? Yes, I have a 1, 6. 1, 4. With 4, do you have anything else? Here I have 4, 4. But this is same as BB, not BC. Okay, so 1, 4 and with 4 I have no other contradictions coming up. So what can I say from here? Here again if you check out 3, 6, with 6 you have 6, 6. That is BB again, not BC. Okay, so that means it is not contradicting anything. Therefore, R is what? Transitive. Transitive. Okay, so here in this question, to check, when we check for equivalence relation, what can I say? Is the 3 satisfied? No. Only 2 are satisfied. 1 is not satisfied. So this is not an equivalence relation. This is not an equivalence relation, but it is reflexive as well as transitive, but it is not symmetry. I believe that you understood this. Just go through this once again. Now let's see another example. See the question. Check whether the following relation is reflexive, symmetric and transitive. Given that R is a relation on set n of natural numbers, defined as R is equal to set of ordered pair xy such that y is equal to x plus 5, and where it is given that x is less than 4. Now here we see that this relation R is from n to n. How do we understand that this relation is from n to n? It is defined that R is a relation on set n. So relation here is from n to n. Now what are the elements that is coming in this relation? Y is equal to x plus 5, that is the condition. So the first element when x is equal to 1, you have y value as what? 6. So the first ordered pair that satisfies this relation is 1, 6. Now next one is when x is equal to 2, you have 2, 7. Then when x is equal to 3, 3 plus 5, you have it as 8. Now what about x? X is less than 4. That means the only 3 ordered pairs which satisfies the given conditions are 1, 6, 2, 7 and 3, 8. 1, 6, 2, 7, 3, 8. That is all that is coming under the given relation. Now let us check for reflexive. For every element A that belongs to this relation, for every element A means what? For every element that is less than 4. Do you have 1, 1, 2, 2, 3, 3? No, isn't it? That means this R is not reflexive. It is not reflexive. What about the next condition to check for? It is symmetry. I have for any AB that is given in this relation, BA also belongs to the relation, isn't it? That is what is said to be symmetry. But here you have 1, 6. Do you have a 6, 1? You have 2, 7. Do you have a 7, 2? Here it is 3, 8. Do you have a 8, 3? No. That means R is not symmetric. R is not symmetric. Now coming to the next one, that is transitive. You have 1, 6. Do you have a 6 with another number? Does the condition of transitivity is satisfied? No. You have 1, 6 here. You don't have a 6 with another number. The condition of transitivity is what? AB belongs to the relation as well as BC also belongs to the relation. Then you should have this AC belonging to the relation. Since when you don't have this BC belonging to the relation, is the condition satisfied? No. That means that it is not contradicting the conditions of transitivity. This relation what I have got here is not contradicting the conditions for transitivity. So what can I say? R is transitive. If it contradicts, then it is not transitive since it is not contradicting. That is, you have AB belongs to the relation. But can you find an order pair BC belongs to the relation? No. That means it is not contradicting the given relation. Now not contradicting the given condition and hence it is transitive. I hope it is clear. Okay, suppose you had 1, 6, 6, 3 but you don't have 1, 3. That makes the relation not transitive. I repeat, you have 1, 6. You have 6, 3 but you don't have 1, 3. This 1, 3 is not there. Then it is not transitive. But here in this condition, in this relation, how the condition comes up? 1, 6 is there, but 6, 3 or 6 with any other number is not there. So there is no contradiction at all. That means it is transitive. When there is no contradiction, we have nothing to say about transitivity. It is transitive. Okay, that's it. Just go through it, children. Now here is another example. Consider. You are going to check whether the following relation is reflexive, symmetric and transitive. Given R is a relation on set Z of all integers defined as R is equal to set of ordered pair xy such that x minus y is an integer. So what is the set Z? Z is equal to, you know that it is minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. Isn't it? And here the relation R is defined from where to where? From Z to Z. Okay. Now here, checking for reflexiveness. I take for every element, for all element A belonging to capital Z, to the set of integers, A minus A is equal to what? For any element A, you take minus 2, minus 2 minus 2, that is minus 2 plus 2. What will you get? You want me to write minus 2 minus 2. That is minus 2 plus 2, which is equal to what? 0. This is for all elements. Whatever you take from the set Z, for all elements A belong to set Z, A minus A, which is equal to 0, is an integer. Isn't it or not? Isn't this statement true? It is giving you a integer. What can you say? For all A belonging to Z, ordered pair A belongs to where? The given relation. What is the relation? Is an integer. Here you get A minus A is equal to 0. Isn't 0 an integer? Yes, it is an integer. It falls in the set of integers. So here A is definitely belonging to the relation. Therefore, what can you say? R is reflexive. Isn't it? R is reflexive. Now checking for symmetry. You see, this is for reflexiveness. Next one is for symmetry. For any A comma B belongs to the relation, A minus B is an integer. What about B minus A? B comma A, does that belongs to R? Is it an integer? B minus A? Yes, it is an integer. So what can I say? For any A comma B belongs to the relation, B comma A also belongs to the relation. A minus B is an integer as well as B minus A is also an integer. That satisfies the given relation. That is, A minus B is an integer, B minus A is also an integer. That is what a relation is. Which implies, therefore, R is what? Symmetric. R is symmetric. And finally, the last one, what is that? Transitive. Now, for any A comma B belongs to the relation and B comma C belongs to the relation. A comma B belongs to the relation and B comma C belongs to the relation. That means what? A minus B is an integer. Isn't it? A minus B is an integer and B minus C is an integer. Isn't it or not? A minus B is an integer, B minus C is also an integer. That is what is given here. AB belongs to a relation, BC also belongs to a relation. That means A minus B is an integer, B minus C is an integer. What must I see? Whether AC is also an integer, isn't it? What I do here is A minus B, I add these, B minus C. What do I get? A minus C. Isn't it or not? When I add two integers, what will I get? I get an integer. A minus C definitely is an integer. When I add two integers, it's definitely giving an integer, isn't it? So, when I add A minus B, which is an integer, to B minus C, which is also an integer, I get A minus C, which is also an integer. So, I come back here. What do I say here? AB belongs to the relation and BC belongs to the relation. Implies what? I conclude AC also belongs to the relation. And hence, what can I say? That is, which implies R is what? Transitive. R is transitive. Am I clear? You want me to explain once again? Check it. That is, it is given that R is a relation on set Z. Z is what? Set of integers. So R is given as, the relation is defined as ordered pair xy such that x minus y is an integer. That's all. X minus y is an integer. And I have Z is equal to what? This is our set of Z. Now, it is given the relation is from Z to Z. For every element that belongs to Z, I can say that when you subtract any two integers, you get what? 0. 0 is an integer. And hence it is reflexive. It is satisfying all the elements A. For every A that belongs to capital Z, A belongs to the relation R. Second, in order to check whether it is symmetry, for any element AB belongs to the relation, for any ordered pair AB belongs to the relation, BA also belongs to the relation. What does it mean? AB is an integer. That means A minus B gives you an integer. What will we get? B minus A is also as an integer. So that means it is symmetry. In order to prove that it is transitive, AB belongs to relation R, BC belongs to relation R, isn't it or not? A minus B, integer. B minus C, yet another integer. For all these A, B and C are belonging to where? Our set Z. Now, A minus B is an integer, B minus C is also an integer. Okay, the condition of transitivity. Now, when I add two integers, what must I get? I definitely get an integer. So, when I add two elements, this minus B plus B cancel and I get an A minus C, which is an integer. So, what can I say? AC belongs to R and hence it is transitive. Okay, children?